Hello, everyone, and welcome back. In the previous video, we introduced a little bit of calculus for parametric curves, and that's the goal for this video and the one that will follow it as well. And previously, we talked about computing tangent lines and areas bounded by parametric curves. Now, what I'd like to do is I would like to extend the notion of arc length, that is the length of a curve, into these parametric curves. Now, the formula in the derivation is almost the same as what we saw with functions, say y is equal to f of x. So I'm going to skip the proof, and I'm going to refer you back to our original lecture with arc length, where I derived the formula for arc length in terms of the Riemann sums. And I am challenging you to see if you can derive the formula that I'm about to give you for the arc length of a parametric curve. Okay, so let me show you the curve, and then we'll do some examples to talk about how to use it. So here we go. Let's give ourselves a definition here. Well, then we say if a curve C, so if a curve C is defined parametrically, so defined parametrically by x is equal to f of t and y is equal to g of t. And we're going to restrict ourselves to a finite range of of t. And we assume that f prime and g prime are continuous. And not simultaneously zero. So this last stipulation that they're not simultaneously zero, this is sort of something that we could probably not think about for a lot of this, but this has to do with higher geometrical aspects of these functions or these curves. So we're not going to touch much on that. I just want to point it out that we don't want these two things to be zero. And C is traversed exactly once as t increases from t equal a to t equal to b. Again, this is a thing that we have to be careful of, right? You think about the circle example. You can just keep going around and around. You can go from t equal to 0 to 2 pi or 0 to 4 pi or 0 to 6 pi. And you're not really counting the curve length anymore. Now you're just sort of wrapping yourself around, right? It's sort of like twine going around a spool. But then let's put this in red to highlight it. The length of C, well, this thing is the definite integral. So the definite integral, which we'll say L is the length. This is a to b of the square root of f prime of t squared plus g prime of t squared. So this is very much like the Pythagorean formula, right? The x component squared plus the y component squared. Again, I offer you the challenge of trying to derive this yourself just by following what we did with Riemann sums for arc length of functions that are that are just y is equal to f of x. Now let's do some examples here, right? Because this is a new formula. But it kind of is describing something that we were already able to do. The point is, parametric curves can describe much more complicated functions or things that are not functions, such as the circle. And so we sort of open ourselves up to finding the length of much more complicated objects. So let's do an example. So example, find the length. So find the length of the circle of radius r greater than 0, defined parametrically by, and we've seen this, r cos theta, cos t, y is equal to r sine of t, and t is between 0 and 2 pi. Now, you probably remember from maybe your first introduction to geometry that the circumference of a circle, so the perimeter, the outer curve of your circle, is 2 pi times the radius. So if we do this right, the length of our curve should again be 2 pi times the radius. Now, what we can see is that we need the derivative of the x component and the derivative of the y component. So let's first compute dx dt. Well, this is minus r sine of t, and dy dt is equal to r cos of t. And so this tells me that the length is equal to the integral from 0 to 2 pi of the square root of dx dt squared plus dy dt squared, which is equal to, now we can sort of plug in what we have, 0 to 2 pi. I get the integral of r squared sine squared of t plus r squared cos squared of t dt. And now we've seen this trick a lot, right? We can factor out an r squared. We get cos squared plus sine squared, or sine squared plus cos squared, which is equal to 1. And so we go 0 to 2 pi square root of r squared dt. Because r is positive, this just becomes r. And so this becomes r from, rt from 0 to 2 pi, which is equal to 2 pi r. 2 pi times the radius, or pi times the pi times the diameter, depending on how you learned this originally. But that's the circumference of a circle. This is certainly correct, at least based on what we were taught in maybe elementary school or high school or whenever it was that we saw this for the first time. Okay, let's go back to our fun example from the previous video, the asteroid. So let's say find the length of the asteroid. So this is our new favorite example, right? This one is, it's just exciting. It's kind of cool looking. It's got a great name. This is going to be our nice classic example to play with now. So we can again take advantage of the symmetries. So we can just find the length in the top right quadrant, the first quadrant, and multiply it by 4. Again, the same thing that we did with the area. We found the area under the curve in the top right quadrant, the first quadrant, and just multiplied it by 4. We can find the length in the top quadrant and multiply it by 4. So let's restrict to first quadrant. And by symmetry, that's the same as restricting ourselves to 0 to pi over 2. That's 1/4 of the domain. And so then dx dt is equal to, and you'll see why I restricted this in a moment, but dx in this case is minus 3 cos squared t sine of t. This is what we got last time when we did the substitution. And then dy dt is equal to 3 sine squared t cos of t. And so in this case, we get the square root of dx dt squared plus dy dt squared, which, after doing a little bit of factoring, so a little bit of algebra here, not too much, 9, let's say cos squared, let's put coses before sines, so cos squared of t, sine squared of t, and then after factoring, we still have cos squared of t plus sine squared of t, which we're all too familiar with, right? We've seen this so many times. This is equal to 1. And so we can get that this thing is just equal to 3 cos of t sine of t. But technically, because I'm taking a square root of that, I have to put an absolute value around it. Now, I don't want to have to deal with absolute values, and neither do you. But luckily, because I restrict myself to the top quadrant, this thing right here, this is non-negative. So cos of t times sine of t is greater than or equal to 0 for 0 less than or equal to t, which is less than or equal to pi over 2. So you were thinking to yourself while you were watching this, you were thinking, what was the point, right? I can just trace this thing around. I can go from 0 to 2 pi, but I had the foresight of having done the problem before presenting it to you. And so therefore I knew that I didn't want to deal with absolute values. And so I can just restrict myself to the top quadrant. And so by doing this, now I have cos t sine t. And so that means that the length of first quadrant portion, well, this can also be computed using the arc length formula. And this becomes 3 cos of t sine of t dt. And in this case, actually, you can use a little trig identity to make this look a little prettier. And you can say that cos t times sine of t, that thing is sine of 2t. So there's a lot of different ways you can solve this integral. Substitution would be fine as well. It's up to you. But we'll have a little bit of fun with the trig identity here. So a double angle formula for sine of t in this case. And then you get a 1/2 that comes out front. That's why there's a 3 over 2. And now we can do a nice integration here. Minus 3 over 4 cos of 2t, and then running from 0 to pi over 2, which now we've got a calculator problem. This thing is equal to 3/2. And so the full length is equal to 4 times 3 over 2, which is, again, I'm just going to draw an arrow so I don't have to write it. This thing is this length right here. Here we have 4 quadrants. Right, that's where the word quadrant comes from, quad meaning 4. And in this case, the total length around this thing is 6 units. Okay, let me show you one more example. And this is actually going to be an example that we can't solve explicitly. So maybe you won't be that interested in it, but it's going to kind of unite a lot of the different ideas that we've had so far in this class. And so let's see. This is example 3. Let's consider the ellipse. So consider the ellipse. X squared over a plus y squared over b is equal to 1. And we're going to restrict ourselves to a is larger than b. And if you pause the video right now and you just type into Google, what is the perimeter of an ellipse? You're going to see that there's no formula, right? So this turns out to be a very, very hard problem depending on the values of a and b, right? So clearly if a is equal to b, then this thing is just a circle. But the deviation between a and b is either going to stretch or compress this thing in each of the different dimensions, the x and y planes, or the x and y directions. Okay, so how are we going to do this? First thing we're going to do is we're going to parameterize this. So let's say let x equal to a sine of t and y equal to b cos of t. It's perfectly okay if you want to change the sines and cosines around. Maybe you're more used to x being in terms of cosines. I just wanted to do it this way because I thought it would be kind of fun, mix things up a little bit. With 0 is less than or equal to t, which is less than 2 pi. Okay, so this clearly implies that x squared over a, should we have this as a squared? Yeah, sorry. The typical way that we write this, pardon me, is over a squared and b squared, pardon me. Then we get this, just so that I don't have to take square roots, right? So if you're annoyed or you're confused or you're bothered by me doing that, it's just so that I don't have to put any square roots in here, okay? So now I clearly have that I've parameterized my ellipse. And similarly, if I take derivatives here, I'm going to take derivatives and square all in one step because the derivatives are very easy. But essentially what I get is a squared cos of t, and then plus b squared sine squared, sorry, that's why sine squared of t. So I took derivatives and squared all in one step. Now, this is just like what we did with the circle, but in the case of the circle, we had a and b are the same thing. They were both equal to the radius r. So we could use the Pythagorean identity. Unfortunately, we can't do that here. So what is it that we can do? Well, we can add and subtract an a squared plus cos squared, a squared plus sine squared, a squared times sine squared, pardon me. So you get this. And then plus, minus a squared sine squared plus b squared sine squared. Now, the Pythagorean identity comes in. We love it. We see it all the time. And so what we get here is equal to a squared. And then we typically, now this is just convention, this is written as a squared minus b squared sine squared of t. So I put the subtraction sign in there. And now, the reason I did this is because this is what mathematicians typically do. We write this as 1 minus, let's say, e squared sine squared of t, where e squared is equal to a squared minus b squared divided by a squared. Okay, so now you're kind of annoyed with me, I'm sure, right? E is not, in this case, like 2.71828, right? The usual number that we deal with all the time. In this case, E stands for what's called the eccentricity. So E is equal to eccentricity. Now, where have we heard the word eccentricity before, potentially? Well, it comes from celestial dynamics. So if you think of the movement of the planets, the Earth moves around the sun in an elliptic orbit. And so what the eccentricity of an orbit describes is it describes your deviation from a perfect circle. So that's why I'm calling this eccentricity. Eccentricity is given as a squared minus b squared divided by a squared. Again, this is clearly positive because a was assumed to be bigger than b. And so this is describing deviations from your perfect circular orbit, okay? So it's important to know that this is not the E that you are familiar with, but that this thing is eccentricity. So it's coming from celestial dynamics. That's primarily where people encounter these things. Okay, so now we need to determine the perimeter of this thing. Well, the perimeter, this is equal to, again, we can restrict ourselves to just the first component from 0 to pi over 2. By symmetry, it's 4 times the integral from 0 to pi over 2. So we're going to keep our lives simple. We don't want to go all the way around in a circle. We're going to go from 0 to pi over 2, and we have the square root of a squared 1 minus e squared sine squared of t dt. which I'll factor out the a squared. So I get 4a, because a is positive. We don't have to worry about absolute values. 1 minus e squared sine squared of t dt. Okay, so you might be racking your brain thinking, how can I possibly ever solve this? And the point is, you can't, right? These are what are called elliptic integrals. So they come from integrating ellipses. That makes sense. These things come up in, like I said, celestial mechanics all the time, hence the term eccentricity. So we don't have a way. I can't just say this is equal to some crazy formula of A's and E's and everything. So what we can do, though, is we can approximate it. And we can approximate it in particular when the eccentricity is small, right? So that means that when we're close to a circle, but not completely there, then we can tell you what this thing is. How do we do that? Well, when we hear the word small, we think of local. And when we think of local, we think of Taylor series. So what we're going to do is we're going to use a Taylor series expansion of that function on the right-hand side. So remember the binomial expansion that we learned a few lectures ago? Well, we can use that expansion. So we can say this thing. Well, of course, this is just e squared sine squared of t squared, which is equal to 1 minus x all squared, or sorry, to the 1/2, pardon me. And then composed with e squared sine squared, right? So we're going to use a composition of a Taylor series from the binomial expansion here. And this is going to give us 1 minus m, which was the power, which is 1/2, e squared sine squared of t. And then minus 1 over 2 times 4, e to the 4, and then sine to the 4 of t, and then minus blah, 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 blah. Okay, I don't want to put more terms into this than necessary. But the point is, this holds, or this converges this converges when we have e squared sine squared of t is less than 1, which is the same as saying the absolute value of e sine of t is less than 1, which means that e is less than 1. Okay, so that is the condition. Your eccentricity can be no more than 1 here. So this is what you're saying. You're saying that this thing is an ellipse, but it's not too eccentric of an ellipse, right? It's not some super flat, long like disc where it's elongated to one direction. It's still kind of close to a circle. And what I mean by close to a circle is as measured by that eccentricity formula that's at the top of the page. Okay, so then, what do we do with this thing? Well, let me start a new page. But my perimeter is 4a, the integral from 0 to pi over 2, and then 1 minus e squared sine squared of t dt, which is equal to, now we can do, we can put in this Taylor expansion. And so we get 1 minus 1/2 e squared sine squared of t minus 1 over 2 times 4 e squared, e to the 4 sine to the 4 of t minus ... and then we'll put dt at the end here. So what we'll do is we'll integrate up the first 3 terms. And it's going to get progressively more complicated because now you're just integrating higher and higher powers of sines. You might have to look these up in a book. They become progressively more complicated, but they're still just trigonometric integrals. You can use the techniques that we presented here in these videos. So let's just do the first few terms. You get So integrating this up and doing the boundary terms gives us pi over 2 for the first term. And then minus, I'm just going to write this out in terms of the multiplications. So just in case you want to follow along and double check your work. And then minus, so the out front are the just constants, sorry. And then in the second bracket in each one of these products is the actual like sine to the power of something, sine to the power of n, integrated from 0 to pi over 2. So you get 1 times 3 divided by 2 times 4, and then times pi over 2. And then, you know, just so I can show you the pattern, you get here, in this case, you'll get 1 times 3 divided by 2 times 4 times 6 e to the 6. This is coming from the binomial expansion. So that's just the constant out front. And then you have 1 times 3 times 5 divided by 2 times 4 times 6 times pi over 2. And then blah, 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 blah. Which is, you know, really, 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 really ugly, right? It's, if you want to clean it up just a little bit by multiplying one of the 2's from out front into this thing, or sorry, taking out the pi over 2's, you get 2 pi a, and then 1 minus 1/2 squared e squared minus 1 times 3 over 2 times 4 squared times e to the 4 over 3. So, you know, I had to multiply and divide by 3 here to make that work. And then minus 1 times 3 times 5 divided by 2 times 4 times 6 e to the 6 over 5 and blah, blah, blah. All right, I'm not going to do any more terms here because it's just going to get super, super hairy. And again, when e is less than 1. Now, okay, what's the point, right? Well, it's kind of cool, right? Because if e is equal to 0, then I get 2 pi a, which is the circumference of a circle, right? So basically what this is doing is this is describing to you what happens if you perturb off of a circle, right? So you sort of take your circle and you sort of slowly start pulling in one of the directions. Then the eccentricity is going to cover that. It's going to quantify that stretching, and you can approximate the circumference of this thing just using a Taylor series. In particular, if you look at this thing, you know, just as the last piece, this is less than 1. This is less than 1. This is less than 1. And so you can compare this to the series e squared to the power of n, where n is equal to 0 to infinity, which converges. And so therefore, this thing converges too, right? So I'm kind of doing some back of the envelope computations now because it's not particularly important. But what is important is that now we've really brought it home, right? We have combined a lot of the ideas that we've presented in this class in order to show, you know, just how to approximate the circumference of an ellipse. So, you know, I hope that this sort of shows you that we can do really, really interesting things with some of these mundane seeming examples that we've done, or these topics that we've covered in this class, right? You might think Taylor series are not particularly interesting, but they are extremely helpful, especially when it comes to approximating things, right? And that's what we saw with the last example in terms of the ellipse.